Good morning to all of you. I hope you all can see my screen clearly and my voice is also clearly audible. It's a fairly good morning today because there is no rain, very dry, sunny morning after a long time. So we take our last lecture on applications of Newton's laws. We will look at some more problems today and some more concepts through them. Then next lecture, that is next week, we are going to start with some new topics. So the first question is already there on your screen. I hope you all can read it. I just readjust. So an adventurer archaeologist crosses between two rock cliffs by slowly going hand over hand along a rope stretched between the cliffs. So here is a two cliffs and there is a rope which is tied and person is going from one end to other. The rope will break if the tension exceeds 2.5 into 10 power 4 Newton and our hero's mass is 90 kg. The angle theta, it should be theta, is 10 degree. Find the tension in the rope. What is the smallest value of angle theta that can have if the rope is not to break? So this is our first problem and now we are a champion. I reiterate my steps regarding solving the problem. So when you apply Newton's laws, what are the important steps? What is the first important step? Can anyone tell me? Certain number of steps are needed to solve Newton's laws. Number 1, number 2, number 3, number 4. That's right. You draw your FBD first. FBD is nothing but a free body diagram. Now there are rules for drawing the free body diagrams. So the rules for drawing the free body diagram is you identify your system. System is the man over here and the rope, and you replace that by a point mass. So I replace that man by a point mass. That's right. That's correct, Warren. You have put all the things, everything in one line. Then you write down in a free body diagram, you have to identify the forces. Remember, one important step where students generally miss is identification of forces. What are the forces working? Now we have already seen some common types of forces in our discussions, and do remember that these will come repeatedly. You should know what their directions could be and how their magnitudes can be guessed. Just to repeat, if there are objects with masses, then the weight has to come. If there are ropes, strings, rods, etc., tension has to come. The rope works vertically downward direction. Sorry, the weight works vertically downward direction. Tension works along the string away from the body. If the two bodies are pressing against each other by any case, then it is normal reaction, which is perpendicular to the surfaces along which the press is happening. And finally, you will get your friction, which is opposite to the intended motion. We have seen one more in the last class, and that is fluid resistance. Fluid resistance comes in various flavors. We have explored one flavor where the resistive force is proportional to the first power of velocity. That is what we will stick to in FYBSc. In Advanced Engineering College classes, you will get many. Fluid resistance is a very important concept in case of automobile, flying bodies, etc. But as far as fundamentals are concerned, even the fluid resistance force proportional to the first power of velocity will explain you all the concepts. So what are the forces working here? So you can see that man has a mass, so the mg has to work in the downward direction, and the rope has tension. So this is tension T. I do not know whether the tension in this part and this part are equal. So I will call them as T1 and T2. Okay, so that's our free body diagram. Next step is you choose your coordinates. It is frame of reference. Of course, along with the coordinates, the frame of reference involves choice of the watch also, or clock, for time measurement. This is a static situation. So coordinate axis choice is tricky here. Remember, I always suggest to choose coordinate axis in such a way that the maximum number of forces get aligned along the coordinate axis. Now here you can see that the three forces are working along three different directions and not perpendicular. So the issue is, how do you choose your coordinate system? Sufyan, won't they be equal since he is in the middle? As of now, it is just a guess, Sufyan. We really don't know. So yes, Roopsa, as of now it is just a guess. We'll try to establish that the tension is same. So the choice of the coordinate system is the next step. Perhaps out of many, one of the choices could be this, that you align mg to vertical. So if there are no other possible choices, you can see, then you choose your x-axis to horizontal and align your y-axis with mg. So this is your choice of axis. Then you resolve forces along the two axes. This is a very important step, and once you have resolved, the original force will go. So example, I can resolve now here. If this angle is theta, then you know that this angle is also theta. So this angle is theta. Resolution is straightforward. The component of T1 in this direction is T1 cos theta, and in this direction is T1 sin theta. Similarly, T2, this is also theta. In direction, this is T2 cos theta. This is T2 sin theta. Now, since it's a static problem, I can now apply the Newton's laws. So then after the resolution is done, remember, once the resolution is done, you don't have to look at original vectors. You have to just look at the resolved vector. These are gone. This is gone. This is also gone. Now you apply Newton's law, which is sigma F is equal to ma. Remember, this is a vectorial equation. You need to use the sign convention. And the next step, as somebody has said, you analyze. So we'll look into this now. We apply the Newton's laws. We can apply along the x-axis. Sigma f of x is equal to max, which is 0 as of now. So this side I can take positive, this side I can take negative. So T1 cos theta minus T2 cos theta is 0. So T2 cos theta can go to this side. Cos theta will cancel, and that will establish T1 is equal to T2. So you can see that we need to establish that, as you people were pointing out. Then sigma Fy is equal to MAY, which is again 0. So the total forces upward is T2. Now T2 and T both are same, so I can call them as T. So my total force upward is T sin theta and T sin theta. So you get 2T sin theta. Total force downward I will get as mg. So T is equal to, or rather I think I want theta. 2T sin theta is equal to mg. So if theta is 10 degree, find the tension. So T is mg by 2 sin theta. So you can put values in this. Here is 90, so 900 divided by 2 into sin 10. This will give you some Newton. And second is what is the smallest value of theta so that it does not break. So 2.5 into 10 power 4 is my breaking tension. So it becomes sin theta is mg by 2t. So 900 upon 2 into 900 upon 2 into the value of the tension is 2.5 into 10 power 4. So whatever you will get a value of sine theta. Theta would be sine inverse. This is how you handle this problem. So once you can see that once you understood these 5 steps to Newton's laws, free body diagram, choose coordinates, frame of reference, resolving forces along axis, applying Newton's laws, and analyze. A friend of mine giving the answer as 2601 Newton. So nevertheless, I hope that's just a part of calculation. I hope you all can handle it. Shouldn't be an issue. Fine, around 2600. Let's go to the next question. We have not taken inclined plane question for a long time, so let us focus on that. We will again remember these 5 steps once again. Yeah, that's fine. That's where those values are fine, Gupta and Rupsa. You can calculate theta later on. So I revise once again. Draw free body diagram. Drawing free body diagram, reduce the system in a point. Identify all the forces. Draw the forces as vectors. Choose coordinates. Frame of reference. Resolve the forces along the axis, x-axis, y-axis. And then apply your Newton's laws for every axis. And then analyze. So let's look at this. Mass M1 is 20 kg and alpha is 53.1 degree. So it's a Pythagorean triangle. The coefficient of kinetic friction between the block and the inclined plane is mu k. So there is a friction between these two. What must be the mass of M2 of the hanging block if it is to descend 12 meters in 3 seconds? So if it has to descend, this is going down, so there is a downward acceleration. So it is already given that there is a downward acceleration of M2. That means M1 will have an acceleration along the ramp in the upward direction. Remember, here we assume that the rope mass is negligible. Also we assume that the rope is sliding over pulley. These are two inherent assumptions, because if the rope mass is not negligible, then you will be in trouble. Can you think why? And if the pulley is not frictionless, again you will be in trouble. And can you think why? Here you need to draw two free body diagrams, one for M2, another one for M2. M2 is going down. So let me first find out the acceleration first. It descends 12 meters in the first 3 seconds. So this is vertical motion. So y is equal to V0 t plus half a t square. Now it descends 12 meters. So y is 12. When it is descending, I guess, so minus 12. It will start from the rest. So initial velocity is 0. So this part is 0. Half a 3 seconds. So 9. So you get acceleration negative 24 upon 9, which is 8 by 3 with the 9 minus. What does minus sign represent? Minus sign represents that it is downward here. So later on we will address that minus sign issue with the help of directions. Navya, you are saying something. If rope has mass, it will also be pulled down and there will be this tension. Yes, I mean if you rope have the mass, then you have to write down, you have to bring in the rope also in your free body diagram. So you have to draw a third free body diagram for the rope. Also, if the rope has the mass, then it will have different tensions at different points, which becomes an issue. So which will require different ways to tackle the problem. Many forces to consider as well as changing mass of the rope, as the proportion of the rope varies across the pulley. That's true. That's true. What happens if there is friction between the pulley and the rope? What exactly does it lead to then? If it is not sliding. So fine, we found the acceleration. It is in the downward direction. That is why it comes as negative. Now we can go for the free body diagram part. So I will draw the free body diagram for M2. Identify your forces. We have revised today. M2G is working in the downward direction and it has a rope attached. So the tension away from the body working in the upward. As I said, since the rope is lightweight, we assume that the tension is same all along. So T working upward. Acceleration is downward. Remember, acceleration has to be shown in the free body diagram and it has to be shown separately. You cannot show acceleration attached to the point mass. To show it separately. Now you can write sigma F. There is only along y-axis. So MAY. So plus T minus M2G has to be equal to M2AY. Remember, this is upward direction plus downward direction minus. Acceleration is in downward direction, so minus. I'm taking negative direction, downward direction from the sign convention. So I will use just the value. Remember, minus here also represent the same. So T is equal to M2 will go this side, G plus G minus AY. So this will help me to get the tension in the rope. Tension T in the rope is M2. M2 is known. Wait, oh, M2 has to be determined. Cool. So T is equal to, M2 is unknown, 10 minus 8 by 3. So 8 by 3 is nothing but around 2.6. So you will get 10 minus 2.6. which is 7.4. So m2 is t divided by 7.4. So I need to find out t. For that I will use the free body diagram for this one. What is the free body diagram for this one? So I think we have seen one inclined plane problem. This is another. So there is a tension, and assuming that the tension remains the same, there is mg, there is tension, there is normal reaction, and then your choice of coordinate axis. Remember, these two are at 90-degree contact forces. So one of the interesting choices could be this way, where you can take this as your x-axis and take this as your y-axis, because in this case you can align the two forces T and N along the two axes. You have to resolve only one. We have all seen the angles in the previous inclined plane problem. This is alpha. This is 90 minus alpha, remember. This is going to be alpha. So I can resolve this by dropping a perpendicular is mg cos alpha, and on this side mg sin alpha. Acceleration is along this direction. So the block is moving along this side. So the friction has to work opposite. Remember, the force of kinetic friction will work. It will work opposite to the intended motion. This is your free body diagram with resolution of vectors. Once the vectors are resolved, the resolved vector is not needed. So mg is not needed. All you can do work is forces which are along the axis. Now you can write your Newton's law here in this case. So let us write it along the x-axis. This side I will take positive. This is negative, upside positive, downside negative. That's correct, Warren. So you can always write sigma fx as max. So plus t minus mg sin alpha minus fk will give you this is m1, so m1a, and sigma fy is 0 because there is no acceleration along this axis, y-axis. So upward n minus mg cos alpha needs to balance. Therefore n is equal to mg cos alpha, which is perfect. Third equation is force of kinetic friction, which is mu k times n, which is mu k times mg cos alpha, and then you can replace this by this fact. So you get T is equal to m1g sine alpha plus f of k. F of k is, you go on this side, f of k is this, so mu k mg cos alpha plus m1a, all is m1. So now everything is known on the right side. Mass m1 is known, alpha is known, g is known. So you can solve this, and you can also use acceleration is also known, because whatever is the acceleration of m2, same is the acceleration of m1. So everything is known. You can find out t. Once you find the t from here, you can use that to figure out your m2. So t upon g minus ay. So this is how you will address this problem. So very straightforward. Drawing free body diagram remains one of the most important parts. One question I had asked you about the pulley. If there is a friction on the pulley, friction between the pulley and the rope, then the pulley will start rotating. And if the pulley starts rotating, then the motion of the pulley should also be taken into account. Look at it. The kind of motion the pulley will perform is a rotational motion. So unless we come to the topic of rotational motion, all our pulleys are going to be static and frictionless. There is another problem which I will devote some time. A block is placed against the vertical front of the cart as shown. What acceleration must the cart have so that the block A does not fall? So this block should not fall. The coefficient of static friction between the block and the cart is mu s. How would an observer on the cart describe the behavior of the block? So we have to look at the cart. We are standing outside and observing here we are, this is V, and observing the motion of the system. So we will draw the free body diagram of the block A standing outside. So FBD for an observer on ground. This is the block A. What are the forces that will work on the block? Let's say the mass is m. So mg is working downward obviously. What are the other forces that will work? There is friction. Which way the friction will work on the block A? What will be the direction of friction on the block A? So if you look at it, observe carefully, think about how the block will move if there is no friction. So you can see if there is no friction, block may fall down. So yeah, so there has to be a friction in the upward direction. So the force of friction here will work in the upward direction. Yes, that's right, that's right. Any other force? Normal reaction. Remember, the system needs to accelerate in this direction. So now you have a straightforward situation. This is upward, this is downward, but up down there is no acceleration. So f of k must balance mg, remember, but f of k is also equal to static friction coefficient into normal reaction. So the normal reaction is mu times, sorry, normal reaction is mg divided by mu. Okay, so this becomes the normal reaction. If you write the Newton's law now along the x, your choice of axis is straightforward. This is x, this is y, and you don't need a resolution because the forces are already resolved. So now if you write down, this is along y-axis I have written. If you write down the Newton's law along x-axis, then only force is N. So N is equal to ma. But N is mg by mu. So the maximum force that will be needed for the system to not fall, a maximum acceleration that is needed, is g by mu. Now what it says is you draw the same thing. How would an observer on the cart describes the behavior of the block? So observer is now on the cart. Suppose observer is sitting here. And this you have to listen carefully. This is now the observer. Static friction, it's not kinetic. Observer on the cart. Now look at it. For an observer who is on the cart, how would the motion of mass m look like? So if you observe carefully, the observer on the cart, m is at rest, because the distance or the separation between the m and the observer will never change. So I'm drawing the free body diagram from his perspective. That's right, Warren. The block is at rest for the observer. So what are the forces working? At rest means there is no acceleration, neither in x-axis nor in y-axis. Forces still working would be mg downward for him. There has to be friction in the upward direction. Two bodies are contact, this is moving ahead, so there has to be a normal reaction. But you can see we have drawn the same diagram here. I forgot to draw mg. So we have drawn the same diagram that induces an acceleration. How do we figure it out? So remember, when the observer is sitting here, listen to me very carefully. When the observer is sitting here, he is in a non-inertial frame of reference. Why non-inertial frame of reference? because the system is accelerated towards right. So in such a scenario, the observer will experience a force which is called pseudo force. You know that we all experience this force. Suppose you are sitting in a car and car accelerated forward, you get a backward jerk. That kind of force. That pseudo force, magnet direction of this force is opposite to the acceleration of the system. So a system is accelerated towards right, pseudo force will appears towards reverse, and its magnitude is mass of the block multiplied by acceleration. So there is a pseudo force that will work towards this side, that is m into a. Now everything balances because block is at rest. Acceleration is 0 here, acceleration is 0. So I can write n is equal to ma. I can write f is equal to mg, which is mu times n. Therefore mg is equal to mu times ma. These cancels. Acceleration is g by mu. So this becomes my acceleration. So you can see the acceleration calculation remains the same, but the two observers really give two different perspectives. And this kind of situation can happen in all the problems which involve pseudo force. So we have, let us see what concepts we covered today. We practiced drawing free body diagram and various forces. Further, we revised our 5-point formulation for application of Newton's laws, and we applied them in different contexts. One thing I forgot here to tell you, to determine cos theta, remember it's a Pythagorean triangle. So Pythagorean triangles, if suppose if this is 3 and this is 4, then this is 5, and this angle is typically 37 point something, you can ignore. This is around 53, which is the case in this problem, 53.1. And so you can now figure out, for example, cos 53 is 3 by 5, sin 53 is 4 by 5, cos 37 is 4 by 5, sin 37 is 3 by 5, etc. So all these you can figure it out. And there we learned the concept of pseudo force. If a body is in a